Hello everyone, my name is Faraz Asim,
And I'm Will Hurley.
and today we'll be presenting our study on evaluating low-cost, customizable 3D printed radius models for three-point bending biomechanical applications. This project is a collaboration between the UT Southwestern Medical Center, Department of Orthopaedic Surgery, and the UT Dallas Department of Mechanical Engineering. Current biomechanical testing in orthopedics relies heavily on cadaveric specimens, which can be expensive, anatomically variable, and difficult to obtain. Additionally, bone analogs are available, but lack customizability and are also expensive. 3D printing has emerged as a promising tool for creating consistent and customizable models. Prior studies have explored 3D printing for the femur, but there is still a need to validate whether these printed models can accurately replicate biomechanical properties of other long bones such as the radius. We hypothesize that in three-point bending, 3D printed radial diaphyses can demonstrate similar flexural strength and flexural modulus in comparison to published cadaveric values. These properties describe the maximum bending stress before failure and the resistance to bending respectively. Our process involved two phases. In the first phase, a de-identified CT scan was processed via 3D slicer and segmentation to produce printable STL files at varying wall counts.
After printing using a consumer-grade FDM printer and PLA filament, 7 specimens with different wall counts from 1 to 7 were evaluated in three-point bending to screen for promising comparisons to cadaveric biomechanical properties. The most promising prints were then tested at larger sample sizes and then statistically compared to published cadaveric values for radial diaphysis flexural strength and flexural modulus. The screening testing identified that the 5, 6, and 7 wall layer samples are most likely to replicate cadaveric radius, flexural strength, and flexural modulus. At higher sample sizes of n equals 10 for each wall count, the 6 wall layer sample was the lowest wall count identified, which demonstrated a flexural strength and flexural modulus without a statistically significant difference from the published cadaveric radius values. This demonstrates that 3D printing, while offering low-cost and customizable bone models, can also replicate the biomechanical properties of cadaveric bones.